All right, the second problem I want to look at here is a tightrope walker. All right. All right. Let's say we have a tightrope walker. They're walking across this tightrope. All right. Their mass is 80 kilograms, and the tightrope makes an angle on each side with the horizontal of theta equal to 10 degrees, right? And I say, okay, you know what? Tell me what the tension in that cable is. All right, so the first step here is always to draw a force diagram. All right, oops, I forgot to do my focus lock there. First step is always to do a force diagram. But what do you make the force diagram of? Well, I'm actually going to make it of that point in the rope. What's happening at that point in the rope? All right, that's kind of a weird thing. Is that an object? Yeah, it's that location in the rope. That's part of an object. So that central point in the rope, right below this person's foot, has a few forces acting on it. It's got an FT going this way, FT going that way. And if it's one rope and it's being bent, then the rope, the tension is always uniform in that rope. All right? So these should be the same tension forces. And then there's the weight of the person pushing down on it. The person is pushing down on the rope, and the amount they're pushing down on the rope with is equal to their weight. Now, I could make a force diagram of the person, and yeah, the rope pushes up on the person equal to their weight if they're not moving. So therefore, the person pushes down on the rope with their weight, right? All right, so I do that. So what we do is put it on a coordinate system, right? That's the first step here. Put this on a coordinate system. And break any vectors into the x and y components. ftx equals ft times the cos of theta. And I don't need to do this twice, right? fty is ft sine theta here. It's just a normal triangle, unlike the last problem there. Cos is the adjacent, sine is the opposite. So our two components are, I'll do it in green here, ftx and fty, right? ftx, fty, those are components. And there's actually two ftys here, right? And there's an ftx going this way. All right. So then we break it into x and y calculations, Newton's second law. And so for x and y, on the right, I have a positive ft cos theta minus ft cos theta equals 0. So I'm skipping writing out ftx plus ftx equals 0. I'm jumping right to what the values actually are here. ft cos theta minus ft cos. Yeah, well, of course, that's a true statement. The y direction is a little bit different, right? And I don't have much room over here. I kind of shifted everything over. Let me move this equation over because it's not particularly useful. So ft cos theta minus ft cos theta equals 0. The sum of the x forces equals 0. So in the y direction, what we have, though, is fty plus fty plus fg equals 0, right? Or what you would say is ft sine theta plus ft sine theta minus mg equals 0, right? So this doesn't tell us anything. If I rearrange this, right, you get ft cos theta equals ft cos theta. You get 0 equals 0, basically, or 1 equals 1, I suppose. So the y direction is really the only thing we need here. So I'll write it a little bit bigger down here. So we add this together, we get 2ft sine theta minus mg equals 0. So 2ft sine theta equals mg. ft equals mg over 2 sine theta. We know theta, we know m. We can solve for the force of tension. All right, so basic Newton's second law type formula. Problem, if you don't know where to start, you start with a force diagram, break any angle of the force vectors into the components, set up x direction, y direction, start plugging in forces, start doing some algebra, see what you have to do to get to the final answer. And yeah, I could put the values in here. Let's see if I have a calculator, right? 80 times 10 divided by 2 times sine of 10, and it's a force of about 2,300 newtons. Pretty big force, you know, 800 newtons of weight pushing down on it, right? So you have to compensate that with the y components of the tension. So the tension is going to be pretty big because the angle's pretty small. In fact, the smaller the angle, the greater that tension is going to have to be. One of the classic things to think about is like if you hang a mass on a string, right? If you have a string, not something at all rigid, you know, like even like a rope, right? If you have a rope and you pull it really hard between your hands and it's perfectly flat, nice and tight, and you hang a rope, you hang a mass on it, is there any way there can be literally no angle here? Is there really any way there can be no angle? Think about that, all right? And we'll talk about that in class, all right? Can this rope stay flat? Why or why not? All right? That's a challenge question. Hopefully somebody will watch this and be able to comment on it.